As you know, we have been doing these activities for the past 1.5 years. So, with the view of informing our members and students about developments in various fields, we have covered topics all the way from quarks to cosmology. So, our idea is to inform teachers and students about developments in fields that are not very familiar to them. That is our idea. At least to tell them about development so that they can follow up, do follow up studies and so on. And it should help in their teaching and research also. This kind of activity is very essential for every university or a college, I think. In developed countries like Europe and America, they do this on a regular basis. Every university will be conducting this kind of outreach activities, connecting their faculty with the general public and the students and so on. A very healthy development, which I think every university should follow. I mean, should take it up. And I am very happy to say, so far as physics is concerned, we have been trying to make an effort in this direction with the cooperation of faculty members from colleges, universities, and research institutes. We are very thankful to them. And one more speciality about our lecture series is that we have conducted some talks in Kannada also, with the view that we should encourage the usage of Kannada, the local language, in higher education also. Because we know from our experience how difficult it is for our students, majority of them, to communicate in English, being a foreign language. So they hesitate to communicate in the language because of difficulties, and we try to help them overcome the difficulties by discussions or teachings in the local language. And even NEP is also suggesting the same thing. So language should not become a barrier for learning. So that is our goal, and then we are trying to do some activities in that direction. So we would help anybody. We would like anybody to give a talk in Kannada if possible, and we have encouraged that also. And since the speaker knows in this particular case, today's case, Professor V.M. Jali, he knows Kannada very well. You can interact with him in Kannada, no problem. So it is an informal kind of series of talks which are aimed at gather information or gathering knowledge about different topics in physics. Okay, with these few words, I welcome the speaker, Professor V.M. Jali, to this webinar series. Before I request him to speak, I'll give a brief introduction to his biography, curriculum vitae, CV. Many of you would be knowing about him. Professor Jali obtained his BSc, MSc, and PhD in physics from Karnataka University. His doctoral work was on the physics of low-dimensional systems under the guidance of Professor Mulimani, former Vice Chancellor of Gulbarga University. In 1993, he joined the faculty of Gulbarga University as a lecturer in the Department of Physics. So prior to 1993, he worked as lecturer in physics at the Department of Physics, Mangalore University also, Mangalore. Now presently, he is working as senior professor at the Department of Physics in Gulbarga. He has 35 years of PG teaching and research experience. His work includes postgraduate teaching, research, and guidance to PhD students and MPhil students. His areas of research include studies on ferroelectric thin films, ferrites, 3 nitrides for photovoltaic applications, and so on. He has published over 53 research papers in various national and international journals. Under his guidance, 11 students have obtained PhD degree. He has established research facilities through funding from Nuclear Science Center, New Delhi, and Board of Research in Nuclear Sciences, Department of Atomic Energy, Government of India. He has completed 4 major research projects successfully. He has visited several foreign countries like Penn State University, International Center for Theoretical Physics, Italy, and he has undergone specialized training on the study of nanoferroelectrics at Nanotechnology Center, Cranfield University, London. He has presented his work in several international conferences held in Canada, Singapore, Malaysia, Pittsburgh, Italy, Kobe, Japan, and so on. He also served as the chairman of the Board of Studies in Physics, Gulbarga University, and head of the Department of Physics during 2016 to 18. He was a visiting fellow of Indian National Science Academy and Materials Research Center, ISC, during 2002, and INSA visiting scientist at National Chemical Lab, Pune. He's a fellow of Karnataka Association for Advancement of Science and life member of our association, KPA, and BRNS, INCA, and so on. He has also worked as a special officer of Gulbarga University Administrative Side, Developmental Administration for Gulbarga University during 2013 to 16. And he has been awarded the prestigious 2015 Material Research Society of India Medal for outstanding contribution in the field of physics and material science. So with these few words, I request him to present his talk on smartness of smart materials. Over to Professor Jali now.
Yeah, thank you, Professor Kagli, sir. Good morning to you all once again. On this webinar platform, I can see senior professors like Professor K.J. Rao. With due regards to Professor Rao, I would like to start my presentation. I have some of my PhD students, my MSc students also, and teaching fraternity from various colleges, where Professor Kagli extended this invitation to give a lecture on smart materials. To give a lecture on any topic of interest. I chose this because everybody wants to be smart. So how exactly we can think of smartness of the smart materials? The big question is whether these materials can replace us with our intelligence, because we are developing these intelligent materials, so-called smart materials. Now we have the era of artificial intelligence, robotics, and all that. So ultimately, they are controlled by human beings. But a time may come where they may start overriding us. So we have to be very cautious. With that in mind, what is that smartness we can think of in the present era of the modern materials compared to the traditional materials? So in the given time of 50 minutes that has been allotted to me, I will try to do justice for whatever presentation I have through the slides. So we always think of Einstein, who said everybody is a genius. His statement goes like this: but if you judge a fish by its ability to climb a tree, it will live its whole life believing that it is stupid. This is what we talk about the genius of the human beings. Similarly for the materials. And there are many smart quotes. A man must be big enough to admit his mistakes, smart enough to profit from them, and strong enough to correct them. I don't want to elaborate on that. Science leads to engineering, engineering leads to technology, and whatever major discoveries have taken place, they are in the 19th century. In the 21st century is the era of the technological advancements. So technology is nothing. What is important is that you have a faith in people, that they are basically good and smart. And if you give them tools, they will do wonderful things with them. Steve Jobs, as we know, he's a college or a school dropout, and how he has made changes. So coming to the contents of my presentation, what are the smart materials? How we define the smart materials? What is that smartness which has self-adaptability, self-sensing, memory, and multiple functionalities? A subgroup of functional materials is what we call as the smart materials. So I'll give a brief introduction. As Professor Kagli has already given a hint to me that majority of the teachers or students, 75% of my presentation will be to the basic level. And even I'm ready to answer in Kannada, as he has already pointed out. 25%, whatever little physics I know, I will try to give justification for that. And why we need smart materials. If man is happy with whatever nature has given, then why we look for materials which are again man-made, synthetic materials, because of our comforts. So how we develop material science as a convergence of physics, chemistry, metallurgy, and engineering aspects, and bring these materials under one umbrella as material science. And there are so many materials. Nothing is a waste. Every material is a useful material. But how we are going to make them useful for us, depending on the environment. They have to sense. That means the materials need to have the brain. They have to have the self-adaptability. Nobody should induce. So how we can develop those materials and what are their applications and recent advances? So giving a brief introduction to these materials, the materials that can significantly alter one or more, like they can change their shape, they can change their stiffness, they can change their viscosity, they can change their response to the radiation. So what are the stimuli and what is the response? We have in physics what is called the law of causality. For every effect, there has to be a cause. So what is the cause? That the material senses on its own, like changes in the humidity. The material should immediately sense that and act according to that. And all these are common features in nature. We always learn from nature and try to go for material synthesis. We can give umpteen number of examples. I will go one by one what we have in nature. So the material has to alter one or more of their inherent properties, inherent characteristic properties on application of an external stimulation. The external stimulation, as I told you, can be change in temperature or change in the humidity, change in the radiation environment, and viscosity change, all these. How the material does these and in a controlled fashion. The several external stimuli to which smart materials are sensitive. It can be stress, like the piezoelectric materials, stress induced piezoelectric effect, which is direct piezoelectric effect and indirect piezoelectric effect. Temperature changes, the moisture content change, the pH of a solution. Especially this is useful, a paint that has been put on a metal sheet. Suppose the metal changes, its pH value will change, thereby changing its color of the coat. Then that is an indication. All these are precautionary measures. Once the damage is done, there is no point in controlling that. Before it starts becoming in a large scale, how we are going to correct that? Then the influence of electric fields, the electrostatic materials, the rheological fluids, the effect of magnetic field change, electric field change. So all these are the different stimuli and what are their responses. It can be changed in the dimensions due to electric field or magnetic field, like we have shape memory alloys and magnetostrictive materials, rheological fluids, ferrofluids, all that. The piezoelectric materials, shape memory alloys, SMA. To SMA, if you add RT, it becomes smart. SMA, RT, shape memory alloys. So they are smart materials. Rheology means flow under the deformative force. How we study. The logy is a study of these deformations that takes place in the fluids. The pH sensitive polymer. There are many polymers. And when I was in NCL Pune, I was working with Dr. Badger, a very small polymer, which is about 1 mm dia. It can blow up to an extent of absorbing more than its capacity, 100 times or 200 times of any aqueous solution. So how it can be used for our purposes? What is the timeline? How exactly, what is the advent of the development of material science, especially concerned with the smart materials? It was in the year 1880 that the direct piezoelectric effect was observed by Curie. Then the shape memory effect, you can see the dates there, 1930. The pseudo-elastic behavior, super elastic behavior that you see in nitinol, nickel titanium naval ordnance lab. It is an expansion for the NITINOL, stands for nickel titanium naval ordnance lab. Similarly, we have terphenol D, terbium iron naval ordnance lab with dysprosium. That is a magnetostrictive material. If you hammer on that with a hammer, the material explodes. It's highly explosive. Like gold cadmium alloy in 1932, the nitinol that I told, NITI, nickel titanium alloy, which was developed in 1963. Then the shape memory polymers. In addition to shape memory alloys, we have the shape memory alloys, shape memory polymers. Then what are the three basic essential components of a smart system? What we need to expect? The first is the sensing property. They can be passive. The smart materials can be active or passive materials. They can sense, like we have panchendriya. We sense. Depending on that, we react. So a smart material need to have a sensation for the surrounding, the ambient conditions. It should be able to receive that information, like your CPU. A computer can only give information to us. We need to process it. that information becomes a knowledge, and then it becomes wisdom. So these smart materials can be said to be wiser. So the next aspect that we expect from that smart material is the processing capability. Hello?
No, continue. Yeah, problem. Some crosstalk. Continue, please continue.
Able to analyze and decide. Decision making is very important. It senses something. There are so many trees which sense the danger. Then they have to take a decision, act upon that. They need to process that information, whatever they have sensed. Then the actuation, the actuators, the able to act on the decision, the actuating process. So sensor, processor, and actuator, these are the three basic essential components of a smart system. Then how the smart materials respond to stimuli, which can be of different types. On the left, I have given a stimulation, the response by the smart materials, how it gives a response. Suppose I take optical fiber. What was the convention earlier in our school days? Light travels in a straight path, rectilinear propagation of light. Now we have the bending of light due to total internal reflection, due to change in the refractive index and all that. Suppose there is a change in the temperature or pressure, or there can be a mechanical strain. How optical fiber responds to that by changing its optoelectronic properties, optical electronic signals. You can use them for display. All these. Then I talk of piezo. Piezo means pressure. Piezoelectric materials with lot of asymmetry in the charge distribution. That is the essential component. If there is a symmetry in the charge distribution, we will not see this effect. So the system needs to have asymmetrical charge distribution. And if it is a stress induced, the commonest example is in our kitchen. Your gas lighter, there is a quartz crystal inside. If you put pressure on that, you get a spark. That's the gas is highly inflammable. It catches fire. That is how you ignite your flames. You get the flames. So it is a stress induced effect that can be leading to electric charge creation, or it can be an electric field, reverse piezoelectric effect that is used for actuation in the computer heads, different where our access is not there through the fingers. Physically, I cannot move any part of a computer or anything. Then I can use it in the reverse piezoelectric effect, as that is called as actuation. The magnetostrictive materials also have that, but the amount of deformation is very less. You can imagine the dipoles, the magnetic dipoles or electric dipoles, if they are randomly distributed, then they take very less space. Suppose on application of a magnetic field or electric field, the dipoles align in the direction of the magnetic field, then there is an increase in the length. So if there is an increase in the length, that coefficient will be positive. If there is a contraction, that will be negative. So based upon that, I can use it as an actuator. Then rheological fluids, especially so in the construction of the bridges, which recently our Prime Minister has inaugurated in Kashmir, the highest bridge, which has taken nearly 15 years or so. Now imagine in the event of an earthquake, how the material is going to absorb that shock as a shock wave absorber. We have advanced so much in science and technology, but for all the natural disasters like tsunami and shock, these earthquakes, we still do not have. We have only limited time of warning, 5 minutes or so, and we have to get ourselves prepared. So how we are going to address that issue? The rheological fluids. I'll give some video pictures also of that. In response to an electric field, by change in viscosity, you have a Newtonian fluid or a non-Newtonian fluid. Water is a Newtonian fluid which follows the Newton's law of flow. There are non-Newtonian fluids, like the morning we start with our gel toothpaste. You are putting pressure on that. The gel will come out of that as a flow. It is a gel. But once it sticks to your toothbrush, it maintains its cylindrical shape. That is a possibility of a solid. So how exactly it responds to that? Like that, we have many examples how the viscosity changes. Viscosity decreases with increasing temperature, and there are materials whose viscosity increases or decreases. And for water, viscosity remains constant. So how this can happen with the iron dispersed in some oil? I'll come to those examples. They are the electrorheological fluids. Then the magnetostrictive material. I talked about terphenol D. In response to a magnetic field, how the mechanical strain takes place, and shape memory alloys in response to the heat. how whether man has the moment I get up in the morning or anybody gets up in the morning, what is that memory? Can we, save that, or can I recollect that? And how many of us believe that we have punarjanma? Yodu janmagalu, and we don't know what was my past or what is going to be my future. In the present only, every day we dream of so many things which we cannot recollect verbatim. I cannot recollect or even copy that. But how the material has that memory that it can regain its shape. I'll give one example for that. And you have thermochromic materials, photochromic, the sunglass, the Ray-Ban glass. So umpteen number of smart materials are there around us, which are man-made, and we have learned from nature. What are their general properties? I can, some of the cartoons I have put slides here, small slides I have put here, bending effect. So flexibility. Can I think of the flexibility in the polymers which exhibit the flexibility? Can I have a foldable mobile in the next few years, which I can wrap it like a pen and put in my pocket? I have shown here pyramids. This has a self-repairing effect. Whatever they have used, calcium carbonate or the limestone, it senses the humidity and it makes a paste on its own, and the cracks are filled. So there is a self-healing effect. ಹಲ್ಲಿಗಳು ಯಾವ ರೀತಿ ತಮ್ಮ ಬಾಲ ಕಟ್ಟಾದ್ರೆ ಅಗೇನ್ ತಮ್ಮನ್ನು ತಾವೇ ರಿಪೇರಿ ಮಾಡ್ಕೋತವೆ. These things are happening very commonly in nature. This is one example that I can show. I have shown optical fiber cable here, how it is used in orthodontics, all that. The essential properties, there are some words here. Transiency, how the smart material should have transiency. That is its response to various types of external stimulation. It can be temperature, pressure, all that. Immediacy, the response and recovery time should be very fast. The smart material should respond immediately. That is called as immediacy. Response time is very less. Self-actuation, it should not be an induced effect. It has to sense from the surrounding and adapt and adopt it, depending on the changes in the environmental condition. Self-actuation, the ability to change their appearance and shape. These are the physical changes. The selectivity, the response is divided and expected. Directness, response is restricted to the activating event. Shape changing, material can change its shape with respect to external stimuli. Self-diagnostic, how many of us can have that self-diagnosis? But doctors will never say that you become your own doctor. Self-diagnostic, able to detect cracks on the material surfaces automatically. The smart windows, smart glasses. Now we have smart buildings. Self-cleaning. You have a huge tower of 100 towers and all that. The Burj Khalifa. From outside, how we are going to clean it? It has to clean itself. So how it is possible? Smart windows. We know the light radiation, solar radiation consists of visible, infrared, and ultraviolet. Infrared is responsible for heating effect, and your ultraviolet is dangerous. So we need natural light, visible light. In addition to that, infrared light also enters inside without spending much on electricity. How we can make the window smart? It has to be transparent, maybe translucent, but it should not absorb the infrared radiation. So the active material should have that sensing capacity to throw away, reflect the infrared part of the radiation. Self-healing, the self-repairing effect. Then I have given here what are the various types of classification of the smart materials. Shape memory alloys, shape memory polymers, SMA, piezoelectric materials, magneto-rheological fluids, magnetostrictive materials, optical fibers, electro-rheological fluids, fullerenes, the carbon, which has allotropic polymorphic nature. Carbon is there, same in graphene, graphite, and diamond. But the arrangement makes the different things, differences in their properties. Graphene, you can think of C60 fullerene, the caged structure, or single wall or multi-wall carbon nanotubes. The strength that they have is more than that of a stainless steel. Imagine the conductivity of them. So how we are going to think of utility of these fullerenes, the buckyball, the smart gels, then the thermoresponsive materials, biomimetic materials. Recently in RCB match, we have seen one kind of an animal which is following the cricket players. Almost it is mimicking the human activity. So how You can have that mimic nature biologically, like what we have for a human being. Then electrochromic materials. There are advantages and associated disadvantages for everything. That is where material scientists comes into picture to overcome those disadvantages for human benefit. The advantage is the compatibility, but they are more expensive because they are not more generalized. If they come into market at a lower price, cost effectiveness is there, then they become cheaper. So compatibility, they have to be compatible, simplicity in their preparation, their compactness, safety mechanism, good mechanical properties. They must be eco-friendly. Whatever we talk should be friendly with nature. You are putting in denture or orthodontics, it should not be toxic. So how we are going to make it eco-friendly? It should not be hazardous to the nature. Longer durability. What is the lifetime of that material that you develop? You invest so much in its manufacturing or making, but it has no durability. It has to be having a longer duration, remote response of the structure, work like a living system. A day may come where it will act like a living system, but the disadvantages are more expensive, low energy efficiency. Ultimately, we need to conserve energy. This is where in smart materials, one form of energy is interconvertible into another form of energy. Energy can neither be created nor destroyed. It is the interconversion of one form of energy into another, what we call as a transducer effect. So, if the efficiency in conversion of that energy, like the photovoltaic effect, why the solar panels have not become so popular? Of the incident solar radiation is limited, maybe 20% or 40%, depending on what kind of a material we use. Then what happens to the remaining photons in the infrared part? That appears as heating the material. So if we can 100% use the photon energy and liberate the electrons from the valence band to the conduction band in a semiconducting material, we have larger efficiency. So how we are going to enhance the efficiency of a material? We need to do materials engineering. Then it has complex control, the disadvantage, limited bandwidth. And they may be, some of them may be not biodegradable. Now we have a biodegradable plastic. It's a nuisance. Plastic is a nuisance now. So whatever we make, like the computer waste, how much is the wastage from each university, each institution, entire country that is at the ocean bed, that is again affecting the marine life. So initial installation cost is very high, like the installation of a solar panel. Unknown long-term effects, we don't know exactly. We cannot extrapolate and say, unless we reach the time scale, we cannot extrapolate and say it will work for these many years and after 15 years, something will happen. They may be causing global crisis, cannot be used for static materials. You can imagine a smart house. You can see the way I have put that. Smart materials are the advanced materials, as I said, functional materials, which fulfills the needs of the current era with their characteristic properties. Extraordinary possibility of materials, which leads to opening the new ways to communicate, translate, like our mobile is a smart material. With mobile, we have become immobile. Everything is at our fingertips now. No, we are neither going to pay current bill to electricity, KEB, nor we are going to post office. Everything is WhatsApp. Now I learned that WhatsApp, you are going to get advertisements in your updates. Again, that becomes a nuisance. So communication you are using, translate, produce, reproduce, and even shortly we are going to have satellite communication for our mobile. Already this Airtel and other companies have already signed an MOU with Government of India. Shortly we may have the satellite connectivity for the mobile communication, produce, reproduce, and automate things and our lives. So you can see a smart house is here. Many a times we as a teachers or students, how many of us are responsive to the power that is on? Fans are on, lights are on, we never switch them off. So how much is going to be the electricity bill? If the system can realize and sense that people have left, it has to switch off on its own. And when people enter that room or a classroom, it has to switch on. That is energy management, energy efficiency. Like that, you can see it can be used as a security system. Recently, my daughter was in US for 3 months, and the house where she was staying as a paying guest completely under CCTV surveillance and automated. And by night 11 o'clock, she felt like it was becoming too hot. She tried to open a window. Suddenly the buzzer started. Three policemen came running. What has gone wrong? So if we depend too much on all these gadgets, then it may be a problem. As a security, CCTV surveillance is there everywhere. How it has become very easier for the police now. But theft are increasing. With all the CCTV and all, people are ready to admit and do all that. Then, as far as comfort for a human being is concerned, a smart shirt. Suppose in a place like Gulbarga where we live, the temperature reaches 45, 43 in the summer. The shirt becomes so hot and lot of dust and your I mean
Sweat.
ಎಷ್ಟೊಂದು ಬೆವರು ಬಿಡ್ತಾ ಇರ್ತೇವೆ.
Sweat.
Sweating. How the material is going to sense and cure itself. Smart finger, smart bracelet. Now many of us have smart watch also. We are not even using our mobile to answer any call. The smart watch will again how many steps you have put, how many kilometers you have walked. Everything is under surveillance. You put any keyword in a Google search, immediately you'll start getting unwanted so many appliances, apps coming. That means somebody is watching us. So smart, it only shows that we are depending too much on materials. ಹಳೆ ಜನಗಳಿಗೆಲ್ಲ ಕೇಳಿದ್ರೆ ಬಗ್ಗೆ ಕೆಲಸ ಮಾಡ್ತಾ ಇದ್ರು, ಎಲ್ಲವನ್ನೂ ತಾವೇ ಮಾಡ್ತಾ ಇದ್ರು ಬೆಳಗ್ಗೆಯಿಂದ ಸಾಯಂಕಾಲವರೆಗೂ. ಅವ್ರಿಗೆ ಯಾವ ವ್ಯಾಯಾಮ ಬೇಕಾಗಿರ್ಲಿಲ್ಲ, ಯಾವುದೇ ತರ ಎಕ್ಸರ್ಸೈಸ್, ಟ್ರೆಡ್ಮಿಲ್ ಯಾವ್ದು ಬೇಕಾಗಿರ್ಲಿಲ್ಲ. Now we are depending so much on these materials and we are going for these extra things. So that we should be very cautious. The Bluetooth key tracker. Even if your mobile is lost somewhere, you can track it. Mobile tracker, Bluetooth key tracker, smart shoes. Many kids you can see for fun. A shoes ಕೆಳಗಡೆ due to pressure, piezoelectric crystal when they pressurize that. Even now many countries are using that to produce electricity. That yesterday I read somewhere they have sold electricity to KEB. Many installations, universities are also selling whatever they generate. Smart socks. ಎಷ್ಟೊಂದು ಜನ ಕಂಪ್ಯೂಟರ್ ಲ್ಯಾಬಿಗೆ ಬಂದ ತಕ್ಷಣ ಶೂಸ್ ಕಳೆದು ಬರ್ಬೇಕಂತ ಇರುತ್ತೆ. ಆ ಸಾಕ್ಸ್ ಗಳು ಇಷ್ಟು ವಾಸನೆ ಆಗ್ತಾ ಇರ್ತವೆ. ಹಂಗವ್ರಿಗೆ ಅದು ಪರಿಕಲ್ಪನೆ ಇರಲ್ಲ. If the socks is smart, then whether it can change that. Smart belt. I'll come to now shape memory alloys. You can see that video. Initially mechanically stretched. Then you put it in hot water like 75 degree. Automatically it regains its original shape. You can see that. It is its initial shape. Mechanically you are stretching it by putting a tensile stress and you are dropping it into hot water. It regains its original shape. So how it is remembering its past? It regains its shape. So it has a memory. It's a nitinol. Nickel titanium, as I told you, Naval Ordnance Lab. This material. So how it is being used? Yesterday I saw one video how we can run a motor without using electricity. Between the two pulleys, one is a bigger pulley and one is a small pulley. You connect them through this nitinol wire, and at the base you put hot water. The nitinol stretches and there is a tangential force. It drives the pulley. Automatically the both will start rotating, and that is how the motor starts. So is it not a novel idea, an innovative idea? So how we can exploit? This is a natural phenomena, but we are going to exploit that for our purpose, for our comfort. So if I give a brief history of shape memory alloys, in the year 1930, Hollander was the first person to observe this effect while working with an alloy of gold and cadmium, AuCd alloy. Nickel titanium alloys in 1960s. And it is a phase change, like austenite to martensite, structural change that makes these possible. Shape changes is a physical change, and it is an intelligent material. It can change to any shape with variation in temperature. As I told you, water is hot. Because of that rise in temperature, there is a regain of the shape. the shape memory effect and pseudo elasticity. They exhibit that. And as I told you, martensite phase is stable at lower temperature. Austenite phase is stable at higher temperature. Examples are given here, as I already told you. Where they find applications. Umpteen number of applications are there for these shape memory alloys. Recently, we had that accident of Air India flight in Ahmedabad. If the wings are like the birds, the bird exactly when it is landing, how it folds its wings, and when it is taking off, if I can make this self-adaptable wings, that your aeroplane wings have to be smart enough to sense that, then maybe this problem would not have arisen. Then in the dentistry, these generally when there is a protruding teeth, generally you put these wires so that due to Newton's third law, there is a reverse third reactive force that puts it in proper shape, in its proper position. So how you can use that? And that wire should not be corrosive. So how it is, I mean, compatible, biocompatible. Then these artificial uh, the tooth, which is endodontic short shape memory alloy tool. Then stunt. Recently, I read an article. ಎಷ್ಟು ಯುವ ಜನರಿಗೆ ಹಾರ್ಟ್ ಅಟ್ಯಾಕ್ ಅಷ್ಟೊಂದು ಯಾಕೆ ಆಗ್ತಾ ಇದೆ? Whether it is the after effect of corona, I don't know. Many youngsters are dying, and they have these problem of. You can think even the pacemaker. It is a smart material. Any ischemic effect, that irregular vibration of the heartbeats, then it will supply a proper voltage so that the heartbeat is regularized. Then you have a stunt that is introduced when the walls are blocked. So if the stunt can expand or contract on its own, cholesterol deposition, if it is too much, then there is a constriction in the movement of that. So how it is going to adjust itself, the size, you can use the shape memory alloys. Then the shape memory bone, the joints that we make, people especially with arthritis, the robotic application, already it is being used in industry. The assembly of these robotics for painting, wherever human access is not advisable, you're using them. The damping effect, as I told you, for the huge construction bridges, on a weak bridge generally we go slow. It is a temporary measurement. But how we can have a permanent solution? The rheological fluid, iron which is dispersed in a solution like water aqueous media, in the presence of a magnetic field, the magnetic iron particles will align themselves and they absorb the shock. And there are certain materials, if you hammer them very slowly, they are soft. If you hammer them too rigidly, then they become thick and resistant. So how you can make use of that? Then even the smart, your glass frames, eyeglass frames, they are made of these smart shape memory alloys, thin film MEMS and NEMS. The nano material is also a smart material. That will take one full hour for presentation on nanoscience and nanotechnology. Then I'll come to the next smart material. I initially talked about the shape memory alloy as a smart first material. The piezoelectric material. You put pressure, then you get the electricity. So piezo is pressure, as I told you, and it was Curie who observed it in 1881. How they are converting? What is that they convert? When you are putting pressure, like on a quartz crystal, you are mechanically stressing that. That means mechanical energy gets converted into electrical energy. A reverse is also possible. On application of a voltage, an electric field, then there can be actuation, mechanical strain. That is, you have a reverse piezoelectric effect that is used for actuation, actuators. So it can be used as a sensing or actuating device. I told you in the initial, sensing, processing, and actuation. There is a direct piezoelectric effect, inverse piezoelectric effect, and examples are quartz, barium titanate, the normal ferroelectric. We have relaxer ferroelectrics like PZT, lead zirconium titanate, which has a diffuse phase transition. Then lead magnesium, PMN, lead magnesium niobate, PZT. Then PVDF. One of my research students worked on this in collaboration with NAL Bangalore on PVDF film. Then where these piezoelectric materials find their application in building, in a smart building, the vibration control, bridge oscillations, how it is going to sense and treat that. Not only sensing and giving an alarm, it has to have that adaptability to absorb that shock and maintain its strength. Condition monitoring, power shoes, human motion, vehicle vibration. Some European countries, like a fast moving vehicle, a lot of vibration is produced. How a material can sense that and generate electricity. Then tire condition monitoring. Before the tire punctures or blast, how we are going to send. That means the flaw, the defects that are present in the interior of a tire, you're not going to destroy that and test it. NDT, the non-destructive testing, before when it is in the molecular level or a very small scale, if you detect that flaw, if you make corrective measure there, then there won't be any catastrophe or a danger. So it is an energy harvester. Then I'll come to the next smart material. I have shown here in the cartoon, there is a random arrangement of the iron molecules, iron atoms there. On application of an electric field or on application of a magnetic field, they align themselves in the direction of the magnetic field. And that is how they are going to act as the rheological material. Rheo, as I said, is a flow. So MRF, it is not your MRF tire. It is the magneto-rheological fluid. A liquid and a gas is a fluid. So it is a smart fluid. 20 to 40% are iron particles, which are dispersed or suspended in a mineral oil or a synthetic oil or even water or glycol. How it can act as a damper. So what it will do, it will change its rheological properties like stress and viscosity. I initially told you Newtonian fluids have viscosity constant. Non-Newtonian fluids change their viscosity. So in response to the stress, whenever there is a stress, like there are super elastic materials. Generally, what we tell for our material science students in my class, elastic has a yield point, then a material enters plastic region, then it enters the fracture region. After the yield point, there is a constant deformation which is irrecoverable. That is what you call as a creep or plastic deformation, depending on the temperature. But here is a material which is super elastic, like a superhero or a superconductor. It maintains its elasticity, regaining its shape and size even when it is in the plastic region. So change in the stress or change in the viscosity on application of a magnetic field is a magnetorheological fluid. What are their properties? They are viscoelastic materials. Materials can be elastic, truly elastic, or partially elastic, all that, inelastic and viscoelastic. Viscoelastic means recovery and some amount of permanent deformation after the removal of the stress. So these magnetorheological fluids are viscoelastic in nature. They have a response to the magnetic field. They are light in weight. They are controllable. The moduli can be controlled and excellent sound absorbing capacity. So you can make it soundproof room. In the picture here, you can see there is a random arrangement and there is an alignment of these on the right side, bottom right, where they find applications. The magnetorheological, this middle one which I have put, the ferrofluid. At the end of my presentation, I have a video for that. You can see how exactly, even we have seen in school, whether the material is magnetic or not, response to the magnetic field, we spread iron particles on a sheet of paper and beneath you keep a bar magnet and move the bar magnet, you can see the shape of the force lines, the magnetic lines of force, which emanate from the North Pole and terminate at the South Pole. So similar things we can see here. I have the video for that. The magnetogeological devices, which are vibration isolators, shock absorbers, and clutch. Then we have these variable connectors, even many who have these artificial legs. Para-Olympics now we have seen for these people, how exactly they function. Then the multiplet transmission form of the magnetorheological brake. In all the present cars, we have the anti-skidding nature. Suddenly you apply a brake, how exactly it is going to absorb that shock and it won't skid. Then I come to the fourth material, the smart material. I'm only giving a brief introduction to this. I'm not going to the in-depth of that. So what are the restrictive materials. The glasses are ultra low expansion materials on heating, like your Borosil glass or Merisma glasses. If I take a material and keep it in a magnetic field, it has magnetic response to that, ferromagnetic or ferrimagnetic or antiferromagnetic or paramagnetic. In addition to that, there can be a dimensional change in the size of the material that is kept in a magnetic field. There can be a little expansion or a contraction. What is that due to? As I told you in the beginning, these have magnetic dipoles. If the magnetic dipoles are at random, then the size is within a small region, they all have distributed randomly. Now, if I apply a magnetic field, these dipoles align in the direction of the magnetic field. So there is an expansion in the length. It is very small, but that is what I call as a magnetostrictive material. If the material is kept in a electric field like ferroelectric materials, then you have electrostrictive effect. So the materials which are magnetostrictive can be magnetized on the application of stress. Stress is a mechanical part, and there is a magnetic response to that. Or it can deform in response to the magnetic field, and these are referred to as the transducers. The change in the length can take place due to magnetization. As I told you, these materials could classify into positive and negative magnetostrictive. If there is an expansion, then I say the material has magnetostrictive coefficient, which is positive. If the material contracts in the presence of a magnetic field, then I say the magnetostrictive coefficient is negative. That means there is a contraction. They can either contract or relax by change in the magnetic field. Then they have a nonlinear effect, the nonlinear characteristics. What is the linear or nonlinear characteristics? If I take a hysteresis loop in a BH curve, if the material is showing a linear response, as long as the magnetic field is applied, the magnetization increases linearly. On reversal of the magnetic field, magnetization also reverses in the opposite direction, but linearly. That means there is no non-linearity. There is no hysteresis. Ends that linear part, it enters into non-linear part. So these materials exhibit that non-linear characteristics. Then there is a frequency dependent hysteresis. At different frequency, they have a different response, due to which we are exploiting that for several changes in their properties that happens due to that they have the complex behavior. Cobalt ferrite, terphenol. See the spelling there, the expansion of that. Like what is the expansion of nylon? It is New York and London. NYLON. NY comes from New York, LON comes from London. These are the two scientists, one from New York, another from London. That is how you get nylon. So similarly, terphenol, terbium, TER, Fe is iron, NOL, Naval Ordnance Lab, and D is dysprosium. So this is a magnetostrictive material. You can watch in Google. It is highly shining in nature like gold. You take a hammer and press that hard, it explodes. So maybe you can use it as an explosive. What are the applications? Tuned vibration absorber, damping effect, then engine mounting as a sensor and energy harvesting. Application of these magnetostrictive materials, the float level sensor, then magnetostrictive transducer, magnetostrictive sensor work. I don't want to go into that. Then I'll come to the next one, the electro-rheological fluids. You can see a video, small video there. Initially, if it is flowing, means it is a fluid. Once it comes out, it takes the shape of a solid. You can see how it drops out there. In the presence of an applied electric field, the black and red you see, they are the positive and negative terminals when you apply a voltage. So this ER, electro-rheological phenomenon, it was reported in 1947 when we got our independence by Winslow. It was observed first in an insulating oil. Oil is a liquid that contains starch or flour, particulate material. So what are the first one was an MRF. Now I'm talking of an electro-rheological fluid. It is a suspension of very small particulates in electrical insulating fluid. When the electric field is applied, they will rapidly form a solid-like structure in the direction of the applied field. the working mechanism, how it works. In an applied electric field, the particles orient themselves in the fiber-like structures like a fibrils. When the electric field is switched off, again they disorient. This is what we see in the students' mentality also. When, whenever the teacher is there, they are aligned. Maybe they are not aligned also. Depends on our ability to control the class, and they disorient. The damping characteristics of it can be flexible, you can make it rigid. A typical example of an electrolytical fluid is a mixture of cornstarch in a silicone oil. You can see when you go to the outskirts, city outskirts, you have huge power lines. How much is the humming sound there? If the outside the noise level is less, you can see a lot of vibration sound. So how we are going to reduce that? You can use these electrorheological fluids that I have shown here. Free vibration dampers, shock absorbers. This video also is there. You can see that later. Then I'll come to the next smart material, optical fibers. The rectilinear propagation concept has gone now. We have total internal reflection due to cladding and inside the material having different refractive index. You can see how exactly light bends. So how you are making use of that? A dielectric material is used, a glass or a plastic. It is light in weight, geometrical flexibility, low attenuation. All that they're used in fiber optic communications now. In the oceanic bed, we have a lot of these fiber optic cables now for digital communication to transmit the power. Applications are advanced intrusion detection for security systems, optical chemical sensors, the laser warfare. Maybe this fight that is going on, now they're talking of nuclear warfare. Whether they go for laser warfare, I have no idea. The optical chemical sensors, optical biosensors used to transmit power using a photovoltaic cell as light waveguides. You can use them. Structural health monitoring, spectroscopy, imaging optics, all that. It is used in surgery also. And this, you can see small video at the bottom. As the temperature rises, see the change in the morphology. Temperature is rising. Bottom right. Is it? Are you able to see that?
Yeah, we can see.
Yeah. When the temperature falls, it recovers, regains. And you have a smart cup, especially for kids. The spoon, feeding spoon, it becomes very attractive when there is a color change. Suddenly, pour hot water or hot coffee in the mug. Suddenly, there is a change in the color. Again, once it cools, some people like to have moderately hot coffee. So, depending on the change in the color, they can sense it. How exactly there is a change in the color of the cup or the mug. So, the response is due to heat. Thermally responsive, it is the ability of a material to change its properties in response to change in the temperature. As we know, glasses and polymers have glass transition temperature, softening temperature in the polymeric materials. The presence of this, the specific volume of the material and its rate of change varies. What varies there? The TG varies, the specific volume changes, and the rate of change of these varies, affecting a multitude of physical property changes. Numerous types of devices could be developed based upon this type of stimuli response behavior. You can use them as thermostat or parts of an automotive and vehicles. Examples are the PEG, polyethylene glycol modified cotton, like heat sensor, the polyester, the polyamide, polyurethane fabrics. So I have given some examples here. The nanomaterials, how we can have a controlled drug delivery. And for cancerous patients, they are using heat treatment. It should be highly localized. And the drug should be released at proper time intervals. Generally, what we do, the problem is elsewhere in our body, but we swallow a tablet in few milligrams. And it has to go through absorption through the stomach and then get distributed. Unnecessarily, we are burdening remaining organs and remaining parts of our body. It has to flow through the blood. If I can directly inject into the diseased part locally, I can cure that. So you can use for a drug delivery system, the therapeutic and imaging, the MRIs, different scannings that people are using. Then I go to the next smart material, the electrochromic materials. The materials, chroma is color or the wavelength. In response to a voltage, how the material changes its properties. That is electrochromic material. It is the ability of a material to change its optical properties, like the color, when a voltage is applied across it. So they can change, they can bleach the color, all these. That is already exploited in LCD, liquid crystal displays, and cathode in lithium batteries. There are different types, type 1, type 2, type 3. I'm not going to the details of that. You can see the bottom right. This one, you can see the change in color there. Suddenly it becomes blue. When it is white, it is fully transparent. It admits. See, we are in a tropical country. We don't want lot, and we have sunlight throughout the year. Many European countries, they starve for the heat. My son and daughter-in-law in UK, they're telling that the temperature has risen to 27, and already the yellow alert is given by UK
No.
government. It is so hot, so extreme heat, but at temperature 27 only, and nowhere there is air conditioning because they have air heating, room heating, because the extreme cold conditions are there, but air conditioning is not there. And see, if the heat enters inside the room, how we are going to block it? A smart window, right? We make it opaque, change in color. I don't want a person inside to be seen. I can change the color. When I want, I can make it transparent. So these, you can use the electrochromic materials, different shading of the window glasses. Then I come to the next aspect, fullerenes, the carbon. See, the diamond is the hardest material. On the Mohs scale, imagine its hardness. Then on the other end, extreme end, you have graphite, like pencil. It's a soft material. Between these two extremities, a soft and a hard, you have the other materials. But the basic building block of that is carbon only. Carbon is there in graphene, carbon is there in graphite, carbon is there in diamond. But one is hard, which has a network structure. Graphite is very soft. It has van der Waals secondary bonding, covalent bonding within the sheets. That is how you can peel it off. And fullerene, the C60 buckyball. So how exactly it can be a smart material, which was first observed by Croto. They are also called as Buckminster fullerene, the buckyball. It can be put in a wrapped in a cylindrical shape, and they have extremely high mechanical strength and lot of high conductivity. And you have the polymeric matrices for the smart systems in electronic and microelectronic devices, MEMS devices. Applications of fullerenes are large as a diagnostic agent in medicine, in cosmetics, biomedicine, as a sensor, photosensitive gas separation, environment, gas storage, lithium ion battery. One of my students who has helped me, two of my students are here helping me in this webinar. One student has completed his worked on supercapacitors. They have high power density but low energy density. How I can have your conventional batteries have high energy density. Your capacitors have high power density, electrolytic capacitors and all that. But can I have a hybrid of these two, like hybrid vehicles? Hybrid vehicles are on the market now. Electric vehicles still they are yet to become popular, but the basic build requirement is the lithium, for which war is going on between Russia and Ukraine for last 2 years, because they have a rich resource of these lithium. So how you can have lithium ion battery, fuel cells, solar cells, electrical devices, photosensitive material, all they have applications. Then I come to the last one. You can see the small video there. This creature you have seen in the RCB match, that is running behind the cricket player. So what are they mimic biologically, biomimetic materials. In 50s, the American physicist and polymath Otto Smith developed this concept of biomimetics. The material and structure involved in natural systems have the capability to sense their environment, process the data, and respond instantly. They could, in principle, be applied in many fields. And because of the diversity and complexity of these biological systems, the number of features that might be imitated is large. The biomimetic materials replicate. Always we learn from nature. We are copycats. CAP, cut and paste. Many things are available online now. So our ingenuity with artificial intelligence and all that, everything you can copy, make your presentations very vivid and very easy. But whether it can replace a human being, his intelligence, is up to us. Applications of these biomimetic material, natural phenomena are many. I told you in the beginning the pyramid, how it heals itself. You learn from the birds. There is one seed here. You can see this. You put it in water, it swells or it contracts. That means there is a response. And even the Kamaladhu, it is hydrophobic. So this phenomena is used based on the contact angle to make the smart buildings, self-cleaning buildings. This is a building in London City, besides the Thames River. Then we have the smart gels. Suppose you put these gels inside a material during its manufacturing, in the event of any stress, so there is a danger. These gel will come out of that and it will heal the cracked region. And you take a polymeric gel, as I told you in the beginning, 1 mm dia, small polymeric gel, put it in 100 ml or 200 ml of water, completely it absorbs. So it can find application as an absorbent, sweat absorbent or a sanitary napkin and all that. It can be made use of that. So smart gels, they shrink or swell by several order of magnitude. They can also be programmed to absorb the release and release the fluid in response to a chemical or a physical stimuli. They're used in areas such as food, packaging. How do I know that the food has become stale? Expiry date is over. In a shop, suppose the expiry date is over. Many of us, we never see the calorie content. We never see the date when it is expiring. Suppose the change in color is there. Once the expiry date is over, the color change in itself, the marketing fellow has to replace it. Or the person who wants to buy it should not buy it. So how it can be used as a packaging material in drug delivery? The concept of these small gels is very complex and all that. I have given an example of PAA, PEO, and so many polymeric materials. Where do they find application? Anti-oil fouling boat. So many applications are there. Drug-loaded hydrogel coated stunt. What are the recent advances? Acoustic energy, walking, smart shoes, dancing, synthetic, self-powered, natural, no e-waste. Earlier we were illiterate, we became literate. Now literate people are illiterate. So how literate people become illiterate? So that the e-waste management is very important, need of the hour. Implantable devices, health, all these I have covered in brief. Again, the list goes on. How we can have a smart hand, flexible shirt, and a person can disappear. We have seen in some of the Hindi movies, a person can disappear. China has already, they claim that they have found out it is a kind of one fabric. You just wear that, you're invisible. The power generating sidewalks in various kinds of application, building, whether in the event of a earthquake, imagine the building has wheels. If the building can move in response to the shock wave, then the building will not collapse. But we don't know from which direction the shock wave comes. Your tire should have the sensing capacity to turn in the direction of the shock wave. This is a big problem in Bangalore, sir. Parking is a big problem in Bangalore. Can I go sideways and park in a very limited space? How much is the torque that is required to take a negotiated turn? So if I can have that sensing capacity of a tire which can rotate 180 degree or 90 degree, then it can adjust itself and you can park it so easily. Again, I have put a list here: tissue engineering, electronic devices, optical devices, drug devices, micro, what is that? Soft, robotics, sensors, stimulation is there. So to conclude, whether am I on to, I've taken excess time? No.
No problem. You can
Yeah.
conclude, no problem.
To summarize, the smart technology, it plays an important pivotal role in developing various novel materials for continuous improvement in the smart materials field for diverse applications. It can be in the field of medicine, industrial applications, commercial, defense, architecture, biology, and environmental engineering, being eco-friendly. They have enormous applications. How much is the research that is going on in various research labs? Current research on smart materials focus on the various aspects: smart textiles, wearable technology, smart lens, the Raman glass. I can give example. Piezoelectric, magnetostrictive, shape memory alloy. All these I have covered in brief. This is a small clip you can see. See how it is a self-defense. A small frog enters and suddenly it closes. So how did it sense that? Ido, touch me not.
Does not plant. Leaf. Smart material. Smart
Yeah.
leaf.
Naturally occurring smart materials.
Smart leaf.
Yeah. How the beads align themselves in the presence of a magnetic field. So always we say structure decides the properties. It is the ordered arrangement of the atoms. That is why the chalk piece is opaque, why glass is transparent, transparent to visible radiation. It is the alignment of these atoms which allow the light radiation to pass through. If there is too much of scattering, there is reflection. Totally, if it is reflected and scattered inside only, then it is total internal reflection, like what you see in the diamond. And this is a fly. Whether our helicopters recently also after the Air India accident, there was another in I mean, what is that? Kedarnath. Seven people died. The
Helicopter.
helicopter fell. See how exactly this fly can change its direction. You are going at 140 kilometers speed on a highway. Immediately, can you reverse the direction? Exactly opposite. It is not possible, but this creature can do that.
They're very smart.
Yeah. So thank you so much.
Thank you very much. Thank you very much. Very exciting talk.
Yeah.
Here are the questions in there. Somebody wants to ask any questions or comments, they are welcome now. Anybody wants to ask question or comments? ನನಗೊಂದು ಕ್ವಶನ್ ಇದೆ. ನಮ್ಮ ದೇಶದಲ್ಲಿ ವಿ ಹ್ಯಾವ್ ಲಾಟ್ ಆಫ್ ನಾಯ್ಸ್ ಎವ್ರಿವೇರ್. ಸ್ಕೂಲ್ ಹೋಗ್ಲಿ, ಮಾರ್ಕೆಟ್ ಹೋಗ್ಲಿ, ಶಾಪ್ ಹೋಗ್ಲಿ, ನಾಯ್ಸ್ ಬಹಳ ಇದೆ ಸ್ಟ್ರೀಟ್ ಅಲ್ಲಿ ಹೋಗಿ. ಸೊ ಅದರ್ ನೀ ಸ್ಮಾರ್ಟ್ ಮೆಟೀರಿಯಲ್ಸ್ ವಿಚ್ ಕ್ಯಾನ್ ಕನ್ವರ್ಟ್ ನಾಯ್ಸ್ ಇಂಟು ಎಲೆಕ್ಟ್ರಿಸಿಟಿ, ರ್ಯಾಂಡಮ್ ನಾಯ್ಸ್.
ನಮ್ ಬಾಯಿ ನಾವು ಬಂದ್ ಮಾಡ್ಕೊಂಡ್ಬಿಟ್ರೆ ದಟ್ ಇಸ್ ಸ್ಮಾರ್ಟ್.
ಅಲ್ಲಲ್ಲ, ಮಾಡೋದಾಗೋದಿಲ್ಲ. ಈಗ ಮಾರ್ಕೆಟ್ ಹೋಗ್ತೀವಿ, ಸಿಕ್ಕಾಪಟ್ಟೆ ನಾಯ್ಸ್ ಇದೆ. ರೋಡ್ ಹೋಗ್ತೀವಿ, ನಾಯ್ಸ್ ಇದೆ, ವೆಹಿಕಲ್ ನಾಯ್ಸ್. ಎನಿ ಸ್ಮಾರ್ಟ್ ಮೆಟೀರಿಯಲ್ ಡಿವೈಸ್ which can convert this random noise, random sound, not in one direction, piezoelectric ಅಲ್ಲ, convert that into electricity ಮಾಡುವಂತದ್ದು ಏನಾದ್ರು ಕಂಡುಹಿಡಿದಾರ, ಮಾಡೋಕ್ಕಾಗುತ್ತಾ ಅಂತ.
That I have to look into that, sir. Right now, I don't have idea.
It would be very useful.
Nothing is impossible.
ಅದೇ ಹೇಳ್ತಾ ಇದ್ದೀನಿ. ಈಗ ಇದು ರೋಡ್ ಅಲ್ಲಿ ಮಾಡಿದಾರಲ್ಲ, ವೆಹಿಕಲ್ ಮೂವ್ ಆಗ್ತಾ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ ಬರ್ತದಲ್ಲ, ಸೊ ದೇ ಆರ್ ಪುಟಿಂಗ್ ಪ್ರೆಷರ್ ಜನರೇಟಿಂಗ್ ಎಲೆಕ್ಟ್ರಿಸಿಟಿ. ಇದೇ ತರ ರೋಡ್ ನಾಯ್ಸ್ ಕ್ಯಾನ್ ಬಿ ಕನ್ವರ್ಟೆಡ್ ಇಂಟು ಪಾಸಿಬಲ್.
Every form of energy is interconvertible.